All right, so I think we will get started. So again, homework 7 is due on next Tuesday. Okay. And for the classroom disinfection today for InSeed, I asked Abby and Jaden. I have to change it because Emma is not here. All right. All right. So we'll start again. Just take a quick review on what we learned last time. So last time we talked about the Hall effect, which is the influence of the external magnetic field to the charge carriers in the conductor. So in that case, there's voltage built up on the two sides of the conductor there. You can use a voltmeter to determine what would be the value of that voltage building up, and then you can also know the polarity of the voltage over there. Okay, so from the polarity, you can tell what would be the sign of the charge carrier inside the conductor. Okay, and if you can measure the voltage, you can also use that to determine a few quantities. Okay, so um, the density of charge carrier, the drift velocity, etc. Okay, according to Hall's effect. We talk about the magnetic force a charge carrying conductor or wire experiencing due to the magnetic field. So that's equal to I times L. I is the current, L is the length of the wire, and then B is the magnetic field, sine of theta, where theta is the angle the wire and the B field makes, okay, or the direction of the current and the B field makes. And if you have a loop inside a magnetic field, so then there will be forces on each part of the loop. So the result will be you might be experiencing the net torque due to the magnetic force. Okay, so the net torque for a loop is equal to the current times the area of the loop times the magnetic field. This is in the case of the plane of loop is parallel to the direction of the magnetic field. Okay. And in general, if the normal direction of the loop and the B field, the magnetic field makes an angle of theta, then the torque will be equal to the current times the area of the loop times the B magnetic field times sine of theta. Okay. And if you have n numbers of loops stacking together with the same current, then you multiply that torque by m. Okay. We also talk about how to determine what's the magnitude of a magnetic field produced by a current carrying wire. So let's, according to Ampere's law. So yeah, I think. So this is what Ampere's law says. So it says that if you do the parallel or this should be the tangential component of the B field along the path, okay, and then add them up. You divide the path into small pieces, you add them up. So, and this is basically doing integration of B times L, okay, but we are not a calculus base, so we are doing just doing it this way, like dividing it into small pieces and add the pieces up. Okay, so basically, in a case of like this, if you have a B field that is circular along a path, circular path, then you do B field times the whole path length. Okay, so B times 2r, 2 pi r, that will be equal to the mu naught times the current enclosed. Okay, and then mu naught is the constant equal to 4 pi times 10 to the minus 7 times T times M over A, okay? Where mu naught is called actually it's not permittivity, it's permeability of the free space, okay? Permittivity is the epsilon, so I think we need to change this guy here. All right. Okay. So then the direction of the magnetic field. So the magnitude is determined by mu naught times I divided by 2 pi r, where r is the distance away from the wire. Direction of the magnetic field is determined by right hand rule 2, where your um, thumb is aligned up with the direction of your current, and then the four fingers curl in the direction of the magnetic field. So in this case, you can see magnetic field produced by a wire. It's a circle around that wire at the center. Okay. All right. So I think that's what we have been talking last time. So today we are going to start with looking at this. If you have a current carrying loop, okay, so we have taken a look at the current carrying wire, the magnetic field it produced. Now let's take a look on a current carrying loop. What would be the magnetic field it produced? Okay, so you can see if you have a loop like this, now we'll be looking at a circular loop over here. So you can see you can use your right hand rule to determine the direction of the magnetic field produced surrounding the loop. Okay, so inside the loop, you can see the magnetic field will go upward if we are assuming the current is in the direction of the arrow in the left figure A. So then inside the loop, you can see the magnetic field go upward. Okay, so but outside the loop, it's going in the downward direction. So this would be the magnetic field produced, okay, by that current. Okay, so it's going in that direction. And then field lines are continuous and they are closed lines. So you can imagine you can feel the rest like by going this guy going backward with a circle like that. My touchpad is not working um, appropriately today. It's kind of too sensitive, so I'm not going to mess up with that. But so you can see that's the magnetic field produced. Okay. Now in real world application, usually you not only have one single loop. Okay. Usually you have several loops or a lot of loops. Okay, stacking together. So in this case, the figure on the left is a solenoid. Okay, that's basically it's a very long wire, but you wrap it around a center cylinder there, and then it forms a solenoid. Okay, so it has many loops there, and you can send in the current from the two terminals indicated by the knobs on the solenoid there. So in that case, you can produce a pretty strong magnetic field in the middle of the cylinder. So that means in the middle of the solenoid. Okay, so you can see the lines in the middle are more dense than the lines outside of the solenoid. Okay. So just outside the solenoid, the magnetic field is almost zero. It's very weak. Okay, you have very few lines there. Okay. So in this case, if you send current I, then because you have so many loops there together, so then that will add up, okay, and then give you a stronger field. So for the magnetic field, you can calculate in the way that if you do if you apply Ampere's law, where you draw a closed path, okay, so you can take the rectangular in the purple color there for your closed path. So then you can see what would be the current is enclosed in that rectangular. So then the current would be those over here. Oops. So, all right. The circles with the dot, that means the current going out of paper, okay, on that part. So you can see now you have rectangular shape. So you have four sides. You can add the four sides up to calculate the B times the length, okay? So when B is parallel to the path, you do the multiplication of the two. So on side one, that would be the B field inside the solenoid times the delta L, okay? And then side two would be the B field parallel to the path times delta L. So in this case, parallel B field is actually perpendicular to side two, the wire. So then that would be equal to zero, okay? In the parallel direction, B field will be zero. So summation of side 2 B parallel should be 0 because B field is in the horizontal direction, wire 2 is in the vertical direction. Okay, side 3, in that case, B parallel just outside the solenoid, it's very weak. Okay, so again, that would be 0 times delta L, so that will give you 0 again. Side 4, as indicated by the numbers there, so it will be again B parallel to the path times the length of the path of the 4, side 4. So B field is parallel, it's in the horizontal direction, side 4 is in the vertical direction. So again, that B parallel will be 0. Okay, so you end up with just B times L. Okay, when you apply Ampere's law here, and that should be equal to the current enclosed by that closed path. Okay, so and times mu naught, the constant number. So mu naught times I, where you should have n numbers of I enclosed by that rectangular. Okay, so that will give you the magnetic field. Then so you move L to the right side of the equation, then B field equals to mu naught times n divided by L times I. Okay, n divided by L. N is the number of loops you have. L is the length of your solenoid. So then that gives you the small n, which is defined as the number of loops per meter. Okay, so that means the density of the loops you would have. So B field then is equal to mu naught times n times I inside the solenoid. Okay, so if you use small n, or if you use capital N, then you should do capital N divided by L. Okay. All right. So this is a magnetic field for a solenoid. And I don't know if I forgot to mention, but a solenoid is just a series of current loops, okay, formed into the shape of cylinder. That's called a solenoid. Okay. Now, for a solenoid, typically it has many turns. Okay, hundreds of turns. Okay. Now, if you have just a few current loops, then we'll just say they are current loops. Okay, but if you have hundreds of loops, then you can call it a solenoid in that case. All right, so we'll take a look on this example here. It says to construct a solenoid, you wrap insulated wires uniformly around a plastic tube, 7.6 centimeter in diameter and 33 centimeter in length. You would like a 3.0 amps current to produce a 2.5 kg magnetic field inside your solenoid. What's the total length of the wire you will need to meet these specifications? So G stands for Gauss. It's also another unit that magnetic field. Okay, for magnetic field. So the conversion from the SI unit Tesla to Gauss is 1 Tesla is equal to 10 thousandths of Gauss. Okay, 10 to the 4th Gauss. Okay, so you may be seeing Gauss as a unit, so but it's not a SI unit. Okay, so you're looking for what's the total length here of the wire that you need. I can give you guys a few minutes to see if you can solve this, and then we can take a look at this together. Okay. We do have several solenoids here in the back. I can grab one. So this is a solenoid we have in the lab. It's actually, so you can see the wires are so thin, you may not be able to see individual one. Okay, so let me see if this camera might be better. Yeah, I can see individual wires that are wrapped around this guy. And they are probably about the same thickness of your hair. You guys can take a look. All right, so on this one, it says you have a cylinder, you wrap the wires around it to form a solenoid. It says if you send in a current of 3.0 amps, okay, so then current goes in there, goes out there. The total length of this tube is given as 33 centimeter. All right, and it says the magnetic field you are producing is 2.5 kilo gauss. Okay, so that's 0.25 in Tesla. All right. Let me see what else is given here. It says the tube has the diameter 7.6. So this is 7.6 centimeter. It's asking you what's the length of this small one. Okay, so the small wire here. So we're looking. Let's call it small L here. Okay, this is the length of wire. Total length of that wire. So we can see for one loop here around this guy. Okay, so if let's say if you have total number of n wires, okay, so this is or n loops, n numbers of loops here. All right, if you have that n, then you can calculate what's the total length of the wire, right? Because each loop will have a length of pi times d, that's the circumference of the circle, right? And times that number of loops you have, that should give you your total length, okay? So your total length is going to equal to total number of loops you have formed times pi times d, okay? times the circumference of each loop there. Now the question becomes, how do you solve for the total number n? All right. So this is a solenoid. So the magnetic field it produces is equal to mu naught times total number of n divided by the length, total length, and then times the current I. Okay. So in here, you can see you can actually solve for your total number of the loops. Okay, from there. Because this is L is given as 33, I is 3, and then mu naught is the constant. So mu naught is the 4 pi times 10 to the minus 7, that constant. Okay. So you can see you can actually solve for your n. So you keep n on one side and then move the rest to the other side. So this to the other side, this guy to the other side, and then L to the other side. Okay. So B denominator here L goes up, and then mu naught times I goes down. They go down. There. That will be your total number of n. Okay. So then your total length L should be equal to this B times L over 4 over the mu naught I times pi times D. Okay. So then you have everything that you needed now. You can plug in the numbers given. So for B is 0.25 Tesla. You convert it into Tesla, the SI unit of it. And the length, total and length should be 0.33 in meters because it's given in centimeters. Okay. Times pi times D given in, again, centimeters, 7.6. So you can do 7.6 times 10 to the minus 2. Okay. To go to meters there. Mu naught is the 4 pi times 10 to the minus 7. The I is 3.0. Okay. Now again, you'll see pi and pi will cancel out. Okay. Yeah. So you can type in your numbers there. Okay. So this will equal to 5.2 times 10 to the third meters. Okay. So that's like 5 kilometers. All right. So questions you guys might have on this? Yes. How do I get number of? Oh, that's a constant number. So mu naught is the constant number. Yeah. Yeah, it's called the permeability of vacuum. All right. Okay. So next section here talk about the magnetic force between two parallel conductors. So showing in the figure, there are two wires. They are conductors. So both carrying currents I1 and I2. Okay. So in this case, I think we have learned so far that if you have a current carrying wire, you will have a magnetic field produced by that wire. Okay. So then there's a magnetic field produced by I1 in figure A, that's in red this time, the B1, okay, the circular lines, they are the magnetic field for B1. And you can see now the second wire that carries current is in the magnetic field. And then we also learned that in the magnetic field, if you have current carrying wire, they will experience magnetic force. Okay, so in this case, if you have two wires, they carrying current and then they are close to each other, so then you can expect there's a magnetic field. each of them. Okay, so to calculate what will be the magnetic field, you can calculate what's the B field at the location of the second wire first. Okay, so that's the mu naught I1 divided by 2 pi r. See if I can carefully move my mouse over here. Okay, so here, so this is B field produced by I1 in the parenthesis. And now for the second wire, it's in the presence of that magnetic field. So the force is equal to I2 times B times L, okay? Because this magnetic field is perpendicular to the wire, the current, okay? So there's no term, there's no, we are not having that term of sine of theta because theta is equal to 90. So that's 1. So if you put that together, then the resultant will be the magnetic force is equal to mu naught times the current, the two currents, I1, I2, times L. Okay, L will be the length of the wire that you are particularly interested in, and divided by 2 pi r. Okay, so r is the separation between the two wires. All right. So in this case, you can use your right-hand rules, number 1 and number 2. You can determine what's the magnetic field experienced by one wire. So we can take a look again on the second wire here. So you use your right-hand rule to determine the B1 produced by I1. So this time your thumb align with the direction of I1, then your four fingers curl in that direction. So that's circular direction. Okay, that goes that way. And to determine the magnetic force, again, you use your right hand, but this time it's a second right hand rule. So, and this time, your thumb again goes in the direction of the current, okay, which is straight up for I2. Now your four fingers that goes in the direction of B field at the point where the I2 is at, the B field is going into the paper. Okay, so in that direction, you can see your so the thumb goes up, the four fingers go into the the paper. So then your palm is facing towards I1, current 1. Okay, so that gives you your magnetic field for this guy, for I2. Okay. And similarly, you can do the same. You can determine what's the magnetic field produced by I2 at location of I1, and then use your, so that's one right-hand rule. And then the second right-hand rule you can use to determine what's the magnetic force that I1 would be experienced due to the magnetic field produced by I2, okay? So that should be in the opposite direction because these two forces are action and reaction pair. Okay, so they are acting on each other in that sense. Okay. So if you have two currents, they are going in the same direction. The force, magnetic force, should be attractive force. Okay. If you have two wires that carries current in opposite directions, you can expect them to have repulsive force among them, between them. Okay. All right. So on this one, let's take a look on this example here. It says two long straight wires are separated by a distance of 9.25 meters. One carries a current of 2.75 amps and the other carries a current of 4.33. It's asking you to find the force per meter exerted on the 2.75 amp wires. And then it's asking you, is the force per meter exerted on the other wire the same, greater, or less to the first one? I think I just explained that second part. So if you have two wires having magnetic force on each other, the magnitude should be the same because they are action and reaction pair, right? It's one object interacting with the other one. So the force will be, according to Newton's third law, should be action and reaction pair. So they should have the same magnitude but opposite direction. Okay, so we can just have part B already answered, but we can take a look on part A. You guys can try to see if you can solve part A. I think I can give you guys just a couple of minutes for that. So it tells you I1 is 2.75 amps, I2 is equal to 4.33. Tells you the separation of the two is 9.25 centimeters. All right. So the force on the two wires should be the same magnitude. Okay, so we will just use F. Okay. So you're looking for force per unit length. So that means you're looking for F divided by L, basically. But you have this equation, right? So you kind of rearrange the equation to get this. So F divided by L then will be equal to mu naught I1 times I2 divided by 2 pi R. Okay. So you actually have all the variables you needed. So those numbers. So mu naught is the constant, the 4 pi times 10 to the minus 7 again. Okay, so that's the number you'll be seeing so often in magnetism here. 2.75, 4.33 divided by 2 pi times 9.25. So that's in centimeter. Okay, you want to use SI unit there. So your 4 pi and 2 pi will cancel 4 pi by half. So you have 2 on top there. So this will give you the force over length, force per unit length to be, I think I got 2.57 times 10 to the minus 5. I would have newtons over meters, okay, for my unit because it's force per unit length. Or you can say this is 25.7 micronewtons, okay. Now also for part B, we have mentioned about that one. So it should be the same magnitude because they are action and reaction pair. Okay. The two forces are action and reaction pair. So they should be having the same magnitude in that case. All right, let me know if you have questions about this one before we move on. We'll be taking a look on another example here. So this one is an example of if you have more than two wires in space, okay, they are close to each other. So there are 3 wires carrying current. So the 2 at the bottom here has the current going into the paper. Okay, so we are seeing the cross. That means it goes into the paper. We are seeing the tail of the arrow. Okay, and then the one on top has a dot. That means the current is going out of paper. Okay, so assuming you can imagine those 3 wires are perpendicular to the paper. Okay, 2 goes out and then 1 goes in. So the 3 sides of the rectangular, those 3 forms are the same. So this is an equilateral triangle here. Now the wire on top carries 5.00 amps of current. One at the bottom carries 10.0 amps. The other one carries 20.0 amps. So what will be, it's asking you to find the direction and magnitude of the force per meter that the top wire experience. Right, so I think you guys can also just try it by yourself first, and then we can take a look at this together. Maybe for you guys to have a couple minutes to think about how you would solve for this, okay? And then we can take a look at this solution together. You are looking for the force per meter on this guy. So that means you are looking for F over L on the top wire here. Okay, so let's take a look at this one together. Okay, so you're looking for force on this wire. Now there are two wires surround this guy. Okay, so you can look at them individually. So for this wire, it will have a force, magnetic force on this one because this wire will produce a magnetic field at this point, and then this wire, because it's current carrying wire, will experience a magnetic force. Okay, so these two wires, their currents are in opposite direction. Okay, so I think when we start with the interaction between two current carrying wires, we conclude that if they are in the same direction, the force will be attractive force. So they are in the opposite direction, so the force will be repulsive force. So you will have a force going in that direction, repulsive. Okay, so pointing away. All right. So I'm going to call this as F1. Okay, and then the force, magnetic force by this wire on this guy, on this wire, will be also repulsive force because one goes in, this one goes in, this one goes out. Okay, they are in the opposite direction. So you have another force there. This is 20, so this would be about twice as big as this one. Okay, so F2. Then your total force would be F. That is the addition of the two forces that wire experience. Okay, now force is a vector, so again you are doing a vector addition. All right, so it says force per meter per 1 meter. Okay, so but for the magnetic force between two current carrying wires is the mu naught times I1 times I2 over 2 pi r. R is the separation of the two wires. Okay, so we can see in this case over here, if we are looking for this I1, just the magnitude of it. Okay, so I1, the magnitude of it should be mu naught I1 I2 over this R. Okay, it's the side of the equilateral triangle, so you can do 2 pi times A. Okay, and times L here, but L is 1 meter, so you can either put L over here or you can just, yeah, replace that with 1 meter. I'm going to just put L over here. Okay, so move L to the left side, F1 over L. Okay, so that's the magnitude we are looking at. So this would be the mu naught, it's the 4 pi times 10 to the minus 7. I1 is 5, I2 is 10, divided by 2 pi times this distance, it's 10 centimeter. Okay, so 10 times 10 to the minus 2, that in meters. So for your magnitude of F1 per meter, that's equal to this 2 pi again will cancel out the 4 pi partially with 2 remaining there. Okay, so this is equal to, actually I don't think you need a calculator for this, right? So 2 times 5 will be 10, 10 times 10 will be 100, and then that will reduce this by a factor of 2, so 10 to the minus 5 over 10 to the minus 2 will be 10 to the minus 3, but that's 10 here, so 10 to the minus 4. So it should be 1.00 times 10 to the minus 4 newtons per meter. Okay, for your F1 per meter, or F1 divided by L. Now you can also calculate what's your F2 divided by L, F2 per meter. This time will be mu naught I1 and I3. Okay, because between I1 and I3, 2 pi A, that's the same. So 4 pi times 10 to the minus 7 T meters over A. The 5 amps and 20 amps.
Mommy's gonna die. You're gonna die, and then you're gonna feel like an idiot. You're gonna be like dying on the floor, and I'm then just gonna be like, damn. I'm gonna be like, damn.
Like totally terrible.
Yeah, on the
Parker,
bright side,
Parker, I'm going to mute you because you are unmuted. He's talking to someone. Yeah. All right. So 2 pi, again, we'll cancel out 4 pi partially. So 2 there. All right. Then you'll have that equals to, this time it's twice of that because this is twice, I3 is twice of I2. So 2.00 times 10 to the minus 4. Okay. So that's your F2 per meter. All right. So now we'll be doing the vector addition. We'll do X component add up and then Y component add up. Okay. So for X component here, it will be this guy over here. And I think it's easy to figure out this is a 60-degree angle, right? Because it's this equilateral triangle. This is 60. Each of the angles is 60 over here. This is horizontal. This is horizontal. So this is also 60. Okay. Now I don't do a good job of drawing a straight line, but this should be in the straight line. So this guy will be 60 degrees. And on the other side here, this should be also 60 degrees. Okay. So then the component, the total force per unit length, X component should be equal to F1 X, okay, per unit length plus F2X per unit length, the X component of the two. F1X should be this guy, the 1.00 times 10 to the minus 4 newtons per meter, okay, times, this is 60, so cosine of 60. Now this F2 is in the negative direction, okay, in the opposite, so minus 2.00 times 10 to the minus 4 newtons per meter times, again, cosine 60, okay? You can use that angle. This is 60, so this is in the negative direction. So that will give you minus 0.5 times 10 to the minus 4 newtons per meter, okay? So that's your Fx add up per unit length. And you'll be doing your Fy L equals to now F1y over L plus F2y over L, okay? So the y component of that guy will be the sine of 60, okay? Sine of 60 plus this time because it's in that direction, so 60, 2.00 times 10 to the minus 4 sine of 60. That will equal to 2.598, so pretty much 2.6 times 10 to the minus 4 meters per second. Not meters, newtons per meter. All right, so you have the x component. This is x component, okay? Fs over L. This is Fy over L. Now, for the magnitude, then you do the x component square. The total magnitude will be your x component square plus your Fy per unit length square, and then take square root of it, okay? So minus 5 times 10 to the minus 4 square plus 2.598 times 10 to the minus 4 square root. That will give you your magnitude equals to 2.65 times 10 to the minus 4 newtons per meter, okay? So magnetic force, it actually is a pretty small force. Okay, you can see it's not a big force. It's -4. For the wires in the range of like 10 centimeters away. Now we want to see the direction. What's the direction of it? Okay, so you can see the theta for a vector should be tangent inverse of its y component over x component. Okay, so this case tangent inverse of the y as this guy, x is that guy. Okay, so 2.598 times 10 to the -4 over -0.5 times 10 to the -4. Okay, so that tells you -79.1 degree. All right. Now, the problem is this x component is less than 0, right? So x component is less than 0. So you want to add 180 degree to it, okay, because of that. So then your final result will be equal to 100.9 degrees, okay? So that's the directional angle with respect to the positive x-axis, so somewhere in that direction. That's the total force per unit length, okay? That's the angle, okay? So any questions you guys might have on this one? All right, so if not, I think we'll just stop here for today, okay? So you can come back on Monday for the lecture.